You want to fine-tune Llama 370B sounds great, right? Until you check the bill. 70 billion parameters, 840 gigabytes of VRAM, 10 A100 GPUs, and 15 to 20 lakh rupees per training run. Most of us can't afford that. But here's the thing, full fine-tuning is wasteful. Researchers discovered that the weight updates during fine-tuning have very low intrinsic rank. In plain English, most of those 70 billion parameter changes are redundant. You're paying for updates that barely matter. Enter LoRA, low-rank adaptation. Instead of modifying the original weight matrix W, you freeze it completely. Then you add a tiny adapter alongside it. The original model stays untouched. Only the adapter learns. Here's the math kept simple. The original forward pass is output equals input times W with LoRA. It becomes output equals input times W, plus input times A times B. A and B are your tiny adapter matrices, and their size is controlled by a single number. The rank R lets put real numbers on this. With a 4096 by 4096 weight matrix, that's 16.7 million parameters. But with rank 16, matrix A has 65,000 parameters, B has 65,000. Total LoRA, just 131,000. That's 0.78% of the original. Less than 1%. One clever trick, matrix B is initialized to all zeros. That means when training starts, the adapter output is literally 0. The model behaves exactly like the original pre-trained model. It can only get better from there, never worse at the start. The rank R is the only that truly matters. Start with R equals 16. If results are bad, bump it to 32. Going above 64 almost never helps. Why? Because the research shows rank 8 to 64 captures 95 to 99% of the information in the full weight update. The adapter, those A and B matrices together, is a tiny file. We're talking 50 megabytes sitting next to a 140 gigabyte base model. And adapters are. Same base model, load a customer support adapter, swap it for a code reviewer, swap again for a medical assistant. Different behaviors in seconds. Even better, you can merge the adapter back into the base model permanently. After merging, there's zero inference overhead. The model runs at exactly the same speed as the original. Just call model.merge and unload, save it, and you're done. Setting this up with Hugging Face's PEFT library is dead simple. Load your base model, configure LoRA with rank 16, alpha 32, target the query and value projection layers, and call getModel. The result? Only 0.17% of parameters are trainable. Quick note on LoRA alpha, it's a scaling factor. The adapter output gets by alpha divided by R with alpha 32 and rank 16. That's a 2x amplification. The convention is to set alpha to twice the rank. Higher alpha means stronger adapter influence. Which layers should you target? For simple tasks like classification or formatting, just target Q and V and attention. For complex tasks requiring domain expertise or reasoning, target all attention layers plus the MLP layers. But LoRA isn't magic. It struggles with large domain shifts, like teaching an English model Japanese. It underperforms on very small models that don't have enough redundancy. And it's better at adapting behavior than injecting entirely new knowledge. Let's recap. LoRA trains 0.1 to 1% of parameters and hits 95% plus of full fine-tuning quality. Rank 16 is your starting point. Adapters are tiny, shareable, and always merge for production to eliminate overhead. And next up, QLoRA takes this even further, fine-tuning 70B models on a single RTX 3090.